but we're scattered across a variety of domains, everything from units to chemistry to physics. And what we're going to be exploring is the entity representation of a number of these different domains. As with the earlier entity presentations that we've given for the version 12 release, we're kind of covering additions that have happened actually over the course of several and kind of culminating in what we have in version 12. So some of this may not be completely new to version 12, but it's kind of a good summary of everything we've got up to this point with some nice additions that are much more recent. So we've got a number of coverage from elementary particles. We've got physical systems, formulas, physical constants. It's kind of related to the unit system we'll be talking about. We've got, as with all the other entity domains, tight integration with the rest of the Wolfram language system using standard quantities, entities, that kind of stuff. And as you can see, we've got particles, isotopes, minerals, among others. Lots of different chemistry stuff. We've already given a presentation on molecules. That was a separate talk. This will be more of the traditional kind of related to chemical data, or what used to be called chemical data, and the entity representation thereof. Also support for proteins. We've got abstract data and formulas. In total, over 300,000 different chemical and physical entities across all these domains, and they're all directly usable through the entity value system. With that, I think I am going to turn this over. Actually, let me do a quick overview just to give you kind of an idea where we're going to go with this. Each row is kind of going kind of from smaller to larger as we go. So we've got particles, isotopes, that kind of stuff in the first row. Second row, we're getting a little bit higher than that. We're talking about kind of structures that form from those, including proteins and crystals. Then above that, we have kind of more atomic physics, kind of lasers, spectral lines, colors, that kind of stuff. And then down at the bottom, it's more kind of very top level stuff, devices, that kind of stuff. And then at the end, we've also got the new unit overhaul that we've done recently. So with that, I am going to stop sharing my screen, and I think I'm going to turn this over to Paco.
Thanks, Jeff. Yeah, hi. So I'm Paco. I'm a research programmer here at Wolfram Alpha, and I'm actually for this. What I'm about to talk about right now, I'm demonstrating a marketing page that was done by another developer who couldn't be with us due to time zone issues, I believe. So we're going to talk about visualizing particle energy spectra and properties. Before we go through this example page, I really quickly want to just give a little bit of a top-level overview of some things of the way the entity system works, just for people who may be watching who are unfamiliar with. So one thing is, we're talking about particles, and the question you might immediately ask is what particles are available, and you can do that with an entity value query where your second argument is entities, and then you just get a long list of them. Now, for people who know about particle physics, you know that, I mean, there's all these hundreds and hundreds of particles. Most of these are going to be your hadrons that are created at a particle accelerator, and they're going to consist of quarks and gluons and things like that. So if we want to get a better sense, maybe a more high-level handle on what's available, it can often be useful, not just in the particle domain, but in any domain, to look at entity classes. So here we have a list. And then if we are drilling down, say we want to look at leptons, we can figure out which entities belong to this lepton class by doing a call like this, where you just call entities, the string entities. Anyway, so that's just an overview on entities in general. But now about the domain particles. This domain is a pretty simple one to explain, I think, because it's largely, we're talking about data that you're getting back, like masses, spins, that sort of thing. It's basically an entity domain that you can think of sort of like a database of data. There's nothing too complicated going on here, but you can get things in a systematic way and create nice plots like this. You can, if you're interested in a particular type of particle, you can drill down to that, the one you're most interested in. One thing I did want to point out is this sorted entity class call that you see here in the middle of the screen right now. That is something, I won't go into the syntax or anything, but I would encourage those of you who are interested in using entities in general to look up the documentation for sorted entity class, filtered entity class, and things like that, because those allow you to do those top level sort of database interesting things in a really nice manner in the Wolfram language. So here's an example where Meng has created a function to get particles with a certain baryon number, lepton number, and charge, and then you can see that it's easy to filter. These little yellow blobs here are the entities. So we're sort of using this to filter through, based on various properties, the entities in this domain. Then we see some nice little charts. You can do this with almost any entity domain. Fundamental particles are, of course, very important to all physics, chemistry, and other things. So we're lucky to have that. And I will now turn the screen over to our next presenter, who is Jeff. Tell me who it is. I'll just stop sharing.
All right, that's me. So sorry about that. Just a little transition here. So I'm going to be talking about the next example, which is exploring isotopes and binding energies. So this one here, previously we're talking about particles. We're moving up here into nuclei primarily. So as with particles, it's mainly kind of a static database type entity collection here. So we've got a number of isotopes here. You can see that you can get the neutron number, atomic number, and whether or not it's stable for any given entity, or in this case, two entities. So here you can see we're actually looking for uranium-235 and 238, and we want to know whether what its neutron number is, atomic number, and stability for each one. You can see both of them are unstable. So we can use that information to then explore all isotopes, not just the two that we specified up above. And from those, we can extract which ones are stable and which ones are not by just a simple cases statement. So this goes along with the earlier thing that everything's integratable into the rest of the Wolfram language. And so then what we're able to do is we can create a list plot. And here you can see this is kind of a standard diagram you'll see in a lot of especially particle physics and atomic physics, especially nuclear physics textbooks, where you see the kind of island of stability running right through the middle here, and then this kind of lighter yellow band going around it that kind of shows the unstable isotopes that kind of go on either side of each neutron number here. So there's that. The next example here, this is one that I have kind of a personal interest in because it actually overlaps a little bit with astronomy. And what we're doing is we're plotting the atomic number versus the binding energy per nucleon for all the isotopes. And what you're seeing here is that when you plot this, where you've got the x-axis is the atomic number here, is that when you get up around here, you get this peak right around in here. This peak is around iron 56, nickel 56, and other similar isotopes. And this has physical significance for astronomy in the sense that all the heavier elements above hydrogen were essentially created in stars and in the cores of stars. And stars can only form elements up to the elements you see up here naturally through core fusion, because above that, the binding energy that you get from getting heavier isotopes is lossy. You don't gain energy by fusing heavier elements than that. And so this is the largest elements that can be fused in the core of the stars. The higher elements are actually done through the processes that happen after stars go supernova. For example, they capture extra neutrons during those violent events and during neutron star mergers, things like that. But this peak actually shows nicely that through the traditional fusion reactions, this is the peak that you would see right around iron 56 and nickel 56. Okay. Yeah. Sure. Sure. Okay. But that's basically about all I've got to say about that one. I'm going to stop sharing, and I think the next person is Jason S.
Yes, we'll move over and switch gears a little bit, talk about some chemistry. So with this being the 150th year of the existence of the periodic table, we thought that for one of the examples, we would talk about the periodic table and see if we could use experimental data to show a connection between the underlying periodicity, which is often difficult for folks that are learning chemistry for the first time to sort of wrap their heads around. So what we did here is to use the data that's stored in the element data And the first thing that we do is we go grab the ionization data, the first ionization energy for each of the elements. And we do that here just as we have seen with the previous examples, taking an entity value call and grabbing the atomic number and the ionization energy. So we do that for we're going to work with just the 54 first elements. We could do this for the whole periodic table, although not all of the ionization energies are known for 118 elements. So we've got the data, and we spit out a plot here, and you can see how it changes. You know, we get the first two, hydrogen and helium, and then we get a next cluster, and then we get another cluster up to argon, and then we get two more rows. And what we start to see is that for the principal quantum number of the valence electrons in each of these elements, we start to see trends. So hydrogen and helium come out with similar values. Then for the n equals 2 row up to neon, we get similar values for the ionization energy, and so on. And so that's, again, showing the periodicity in experimental data, which, again, harkens all the way back to how the electrons fill in their orbitals. So then we wanted to look at other properties which are contained in chemical data and element data. And here we go, rather than looking at the ionization energy, we move over to atomic radius. And again, we can plot the atomic radius. And what you see is a little smoother plot as we move again from the n equals 1, so hydrogen and helium. Then we move to the second period in the periodic table, and we see a nice curve from lithium all the way over. And then we continue in the third row, in the fourth row, and lastly in the fifth row. And even if we hadn't had Mendeleev to order the periodic table for us, we could start to take this data, and if we think about it a little creatively, we could start to see some of the arrangements, or at least that we see the elements falling into distinct rows. If we rotate the data, as we say here, where we've now put the atomic number on the left-hand side of the plot and the radii at the top, and you can see that if we get rid of the extra labels and whatnot to simplify the plot, we start to get a row of 2 atoms, a row of 8 atoms, a row of 8 atoms, and we get a row of 18, and then we get a row of 18. And if you were a little bit creative and you kind of squish and readjust the size of the plots, what we could eventually get down is some arrangement where we have a row of 2, a row of 8, another row of 8, and 2 rows of 18. Again, starting from experimental data, in this case, either the ionization energies or the atomic radii, and show that we sort of get the structuring that we see in the modern periodic table. So not only do we have information on the elements, we also have information on molecules. And so let's move over to the next example, which is how we can investigate some of the melting and boiling points of chemicals and show how those vary across the molecular mass. So again, just a reminder for those of you that are new to the Wolfram system, you can type in an entity and then ask for its property and square brackets behind it, in this case density, or maybe the IUPAC name. I won't read that off, it's quite the mouthful. But using chemical entities, we again also have entity lists. So we have the molecules organized into groups, such as in this case alkanes, or inorganic molecules, or organic molecules. We're going to look at the alkane list, which it turns out we have 433 alkanes in our chemical grouping. And we can quickly look at some of those. We won't look at all 400 of them, but we could look at, say, 20 of them. And as you see here, we can get the 3-dimensional plots to see their different shapes and the way that the carbon and hydrogen molecule, or atoms in the molecule, are arranged. Clearly, we have quite a variety of different shapes. And now we can then look at the properties of those molecules. In this case, we're going to look at the molar mass. And here we can plot how the molar mass changes. And the number of, as you see, we have quite a few molecules that, in the alkanes that come in around about 100 grams per mole, and less as we go out to larger molecular masses. We can use entity functions and select more specifically the entities that we want out of the large collection of chemicals in the Wolfram knowledge base. And so here we're going to look at all the alkanes, and we're going to just plot their melting points. So this is all 400 some alkanes plotted with their melting points in Celsius. And you see it's rather busy. There's a lot going on. A couple things jump out at us that adamantine and camphane have rather high melting points. And you can see that we can go and look at their other properties, which in this case is a molecular plot again, to see if that gives us some information on what's going on in the molecule for why they might have such high melting points. And in this case, we see that adamantane and camphane both have bridge structures and rings, which change the physical property that we're looking at, the melting point in this case. We can get more specific rather than just looking at all 400 alkanes. We could look at a different class, a subset of that alkane group. We could look at molecules with the formula CN and H2N plus 2, more of the straight chain alkanes. And we do that here again. We're going to build an association. We can use entity functions to select out the molecules that we want. And now we have a list that's only 231 molecules, excuse me. And we plot that, and again, we see a much more clearer trend as the carbon atom count, and therefore the molecular mass of the molecule increases, the melting point increases as well. One way of understanding this is that as the carbon atom count increases, the molecule gets bigger, and the amount of dispersion interactions between the individual molecules increases. Therefore, we see higher melting point. We can go down and look at other properties, in this case, the boiling point, and we'll see the same sort of trend happening. It's a little cleaner in this case with the boiling point. Again, as the carbon atom count increases, then you can see how the melting point again increases almost linearly with the number of carbon atoms, again, due to the London dispersion and van der Waals interactions between the larger molecules driving up the melting point. And there is a question. Still be this. You could preload the data into. So the question was, is there a way to get at the properties for all the molecules faster? You can make sure that you've loaded up into your notebook, and use entity prefetch. But that's about it. So, and of course, you can use smaller chunks of molecules. So doing them in smaller batches if you're having particularly long delays with using hundreds or thousands of molecules at a time. But with that, unless there are other questions, I'll hand it back off to Jeff to go back to some details of minerals.
Okay. So back to me again. Let's see, I'm just going to go back up to the top here and then click right here. So as Jason mentioned, here I'm going to talk about minerals. So this is a domain. It's a general kind of database type thing where it's kind of curated properties, not a lot of computational type things in here, but you can see we've got a lot of different entity classes as we do in the chemical domains that Jason just talked about. So you can see just a set of the ones that we have in mineral data here. You can look at some of the formulas that represent some of these minerals. Look very much like a chemical formula. In this case, they tend to be mainly not so much, you don't get a lot of carbon atoms and stuff in here. Minerals tend to be more metal based, and you don't I don't believe minerals even officially can be organic in nature. So all the ones you're going to see here tend to involve things like sodium, manganese, aluminum, iron, things like that. And they can get rather complex, as you can see in some of these formulas. Here you can see, and I should mention that these callouts, and Jason showed some in some of his plots, this is one of the newer features in version 12, and it's a quite nice feature, is that we have automatic layout for callouts. And here you can see we've put a callout here on the data that we're plotting, where we're including density, unit cell volume, and then the entity itself. And this is what allows the call out to work and label it. So here you can see the position on this, where we have the density and unit cell volume and cubic angstroms on the y-axis and grams per cubic centimeter on the x-axis. And you can see where the various minerals fall. So something to keep in mind is that if you do this actually in Mathematica, it will label what it can, but if it finds that area is too dense to label everything with a call out, you'll automatically get a tooltip. So you can still hover over the individual points and find out which point corresponds to which entity. So something nice to play with in version 12. Something else that we're doing here is pretty standard when it comes to minerals. You want to know the Mohs hardness. It's one of the older, more traditional ways of measuring how hard a given mineral is versus its density. And you plot the two versus each other, and you can see kind of where most of the minerals fall. You can see that most of them tend to fall in this kind of 2 to 4 area, but you do have a separate cloud up here and stuff. So it's kind of neat to just from almost a cluster analysis point of view where the various minerals fall. Moving on from that, we've actually got, this is kind of it's kind of tied to mineral data, but it's kind of more of a recreational form of it. And this is famous gem data. This is a rather small entity domain, but one of the reasons that I wanted to include it here is because it provides a nice example of how you can use the properties of one domain to then drill down into the properties of another. So this is what we call chaining. So here you can see I've asked for the Hope diamond. I'm getting its mineral type. And from the mineral type, I can also ask for the crystal system of that mineral type. And that's actually a different domain. So here you can see that it comes back and says it's a cubic crystal system. So here you can see where I've drilled down here several levels. I've got the Hope diamond getting its mineral type and the crystal system of that. And from that, I'm getting the Brevet lattice and then an image. And so you can kind of see the different types, not necessarily of the Hope diamond, but of the crystal system that it belongs to. There are several Brevet lattices that you can get, and here's what they look like. But even without chaining, you can find a few interesting facts about famous gems. Like I said, it's more recreational. There's not a whole lot of data other than the weight and the uncut weight. And here you can kind of see that they're, surprise, surprise, kind of linearly associated with each other. So when they first find a famous gem, it often gets split up and broken up into smaller pieces. And we can actually sort. Here's an example showing that we can use tally and data set combined with the mineral type to find out how many in this collection are of what type of gem. So here we've got most of the famous gems tend to be diamonds, but we've got a lot of famous pearls, topaz, things like this. Famous gems aren't really, there's not an official catalog out there, so there's probably a lot of famous gems throughout history that aren't properly recorded. So it's kind of interesting to try to track that information down. At this point, I think I'm going to pass it to another Jason. This is Jason Biggs, and I will stop sharing here and allow him to take over.
All right. Thank you, Jeff. Let's see. So yeah, now we wanted to switch gears back to, let's see, not quite back to chemistry, but into biology. So now we want to talk about, let's go back to the main page and show the icon. We always spend a little bit of time on these, on the icons. So, so this is discovering the structural complexity of proteins, and so we're exploring the protein entity type. So in this, we've got a lot of information which we've taken from various sources on the webs about proteins. I always like, when looking at a domain, to look at the properties available. So to do that, you can use the function entity properties, and it's a nice function it takes advantage of the autocomplete features here. So I just start typing protein, and I can see all the different domains. It's some discoverability there. And so the types of properties you've got available include like molecular properties, the weight, also what kind of functions does it do, information about the IDs, the URL for the entry in the protein data bank, some secondary structure rules telling you where helixes and beta sheets are. And once you get these properties, if you want to you can access them through the yellow boxes, right? So so that's what we call these. This is the formatted form of an entity property. You can also just type in the string. So you can use canonical name to find out the string that represents the given property. Okay, so now back to the example. So you can get a nice image for every protein just using just taking 3 random proteins and going for the ribbon diagram property. And those are attractive. And then you can do some computations to compare different properties with each other. So here we look at the molecular functions and the secondary structure rules. So the molecular functions is like a description of what the protein does in the cell. And so, yeah, that'll be things like cathepsin F activity, the ferric ion transmembrane transporter activity, and such. So, so first you do entity value of protein and then a list of properties, and that gives you the properties for every entity in the domain. And then you call delete missing here because there are a lot, 54,000 proteins in the Packlet, but quite a bit of missing data. So you get the proteins where we have all of this information are going to be the more common proteins. And so we call those the common proteins, and with their molecular function and their secondary structure. And then you can count the number of secondary structures. So the secondary structure for how does that come through? So we pick a random entity protein, and then we ask for the secondary structure rules. Like I said, sometimes it is not available. Okay, so that's funny. I should have prepared that example, but we have a prepared example here. So if you count the number of secondary structures for every protein, you can get this information in an association. Then you can group them, figure out the mean number of molecular functions for each protein, and then compare them like this. And then gather more information in an association, and then finally look at the plot. So that's the protein entities, and now we look at another couple of domains: the crystal systems and the crystal families. And so in a crystal system, we have a set of point groups and their corresponding space groups. You can see these are small domains. There's only 7 and 6 entities in each domain, and they have a list of properties. You can get those properties and put them in a grid. And similarly, you can look at the edge and angle data and edge relations and such. All right, so with that, I'm going to stop and pass this on over to
our last Jason, I believe, which should be me. Yeah, so the theme of this next line of examples is light and color and that sort of fashion. So we start off with laser wavelengths, and we have a nice little collection of data on lasers, which cover a range of wavelengths and excitation types, different methods for constructing these lasers. You can use this to find out what a typical laser of this type would have in terms of its wavelength. And you can also have a nice visualization of the range that these lasers cover. So here we have just the lines indicate what wavelengths are covered by the lasers, and we're going along nanometers, and it covers quite a large range of wavelengths, down to the very small to the very large. If we want to, we can look into a specific region of that spectrum and find, say, all the lasers that have visible wavelengths. So some copper lasers, and neodymium, krypton ion. And we can do a visualization of that where each of the wavelengths is then colored according to what it would actually look like if you were to shine this on something, not your eye, let's say, but shine it on something and see what color they are. We also have a nice little visualization here just showing what the different categories the lasers fit into. So we have a lot of gas lasers, a lot of optically pumped lasers, and DC excited lasers. And that's pretty much it for lasers. Now, in terms of spectral lines, which is to say the lines given off by excited atoms, we have a much broader data set. We have, let's see, I'm just gonna jump over to here. So we have 250,000 atomic lines available. We also have the levels that these lines jump between, and that covers over 100,000 different atomic energy levels. And we can use these to look at a wide variety of properties. In fact, look at some of the properties that we have available for atomic lines. And these cover most elements. This comes from the NIST database. Pretty much covers all of the longer lived elements and many isotopes as well. So let's see if we return to our examples. So here we're looking at a specific element, hydrogen, in the visible spectrum, and getting a list of, I'll get some questions here. Oh, okay. It's handling that. So this is a list of all of the hydrogen lines for neutral hydrogen in the visible spectrum. And if we query a specific atomic line, we can get a data set, and it'll show us all of the properties for which we have data for that particular line. So that includes not just the wavelength, but the energy of that wavelength, what the upper and lower levels are if they're known, the NIST identification number if you want to reference that, what type of transition type it is, and in many cases there'll be some notes about what the precision is or what the transition probability and strength are. So we're going to go back to that nice visualization of a periodic table. We're going to expand it a little bit more. So we take an association to define our boxes for our periodic table. And then what we're going to do is we're going to take all of those lines within the visible spectrum for all of the elements. And then we're going to then take all of those atomic lines and find what color they correspond to, and we're going to make a periodic table that consists of all the elements showing their visible spectrums. So for some elements, those are going to be pretty sparse. Hydrogen, helium don't have a lot of lines that lie within this visible spectrum, but other elements can cover quite well the full spectrum, especially down here in the transitions, so like iron or things like that. we'll have hundreds or even thousands of lines in the visible spectrum. So moving on to something a little separated from spectral lines, but still quite related, colors. So in the Wolfram language, we have data on not just colors, but also color sets, say the set of all red colors, the set of all blue colors, and color spaces. So this is if you're to visualize colors in space covering all colors. This would be your chromaticity plots, your RGB space, any of those sort of methods of describing colors in terms of some sort of primary colors or hue. So here we're looking at the spectral colors, so violet, blue, cyan. We have some other sets of colors that have been added, such as, let's see. Let's see. So things like cream and gray and blacks and whites are also available. But we're going to restrict ourselves to the spectral colors for now. And then we also cover a variety of different spaces. So this is looking at what percentage each of these sets cover within a given space. So we just quickly query that, and we can have do some plotting, some of bar charts. And in different color spaces, these color sets are going to cover different amounts of the volume of those spaces, because different color spaces will devote larger regions based on how they're constructed to these different sets of colors. So RGB is going to cover cyan to a much larger extent than, say, sRGB or an XYZ space, which is more centered on green. Now, turning to colors themselves, in the Wolfram knowledge base, we have thousands of colors, not just things like green and blue, but also colors from different collections. This is the Benjamin Moore color set. And we have quite a wide variety here of different colors. And we can use these in our calculations. Here we're defining a function that takes a list of colors and then an image, and it uses that list to create a nearest search. So it'll look for each pixel in that image. It will look for what is the closest color in that list that you've provided to that pixel, and then replace it with that color. So here we have an example where we're going to take American Gothic, and we're going to replace it with the Benjamin Moore historical color collection. Not quite the best side-by-side comparison here, but you can see a difference there between the colors. It's even more extreme if we restrict ourselves to their signature color collection, where we lose a lot of the color detail because we're working with a more restricted color set. In fact, if we take a look at that, to find out the length here, we have 100 colors in the Benjamin Moore signature color set. Whereas if we were dealing with the other color set, we would have something, yeah, we have twice the colors in the historical color set. So you can see just restricting yourself to a smaller set is already going to impact the image that's presented. Now, the other thing that this function that we've defined does is it looks at how much of each color is used to replace pixels on this image. So we can see which ones dominate in doing the replacements. So here we see we've replaced a lot of the pixels here with the blacktop color, and relatively few with these more sort of brownish colors like Villa or Prairie Lily. So that's what we have to say about color at the moment. And to bring us to end of our light theme, we return to the atomic spectra and to focus on atomic levels. So here we're going to look at the transitions of helium within the visible spectrum. So as I said before, we have all of the energy level data from NIST's atomic spectra database. So 100,000 plus atomic states. And we can find out things like how much energy they have. I think I briefly already went over what their other properties are. So you can find out their quantum numbers, term symbols, all of that important quantum mechanical information about each energy level, in addition to just how much energy they have. So we're going to visualize the jumps between energy levels in neutral helium that lie within for lines that lie within the visible spectrum. So we grab all the lines within the visible spectrum. We can then grab their upper and lower wavelengths. We'll also grab their observed wavelength so we can determine color information. We'll extract out their value of those wavelengths in nanometers, which we can then feed to the color data visible spectrum function. And then we can create a nice little visualization of those atomic lines, just like we had done in our earlier example. But now we're going to also grab those levels, and we'll find their names and energies. And we'll use that information to construct a nice little plot that'll show energy levels connected by where each of the lines is connected by a line. So essentially we have our lower level and our upper level, and we've connected it with the line corresponding to that jump. So they're colored according to their wavelength. But we can pretty this up a bit by grabbing all of the energy levels and selecting out those that lie within this energy range. So between 21 and about 25 electron volts, or it's about 24.3. And then we can plot them alongside using them as grid lines. So we can see that not all of the energy levels in this region are covered by these transitions. Some of these are just not allowed because they don't have the appropriate spin quantum numbers to allow those transitions. They might be involved in other transitions where we don't have to, where we're not changing the spin in a way that's not available to us. But for jumping between energy levels in this regime, there are none that are allowed. And these actually make the bulk of the energy levels that we have available in this area. It's about 2/3 are not in that allowed category. It's actually sort of a subset in any particular area. They allow it to jump, that can jump between each other. All right, now we're going to shift focus. And these next two examples deal with measurement devices. So the Wolfram language includes information on a wide variety of different measurement devices, everything from yardsticks to particle detectors. In this particular example, we're looking at pressure measurements and looking at what is the range of pressure measurement devices that we have available here. So we can ask for, well, how many pressure measurement devices do we have information on? We have 34, and then we can look at their normal ranges. So for a piezoelectric sensor, that can be a normal sensor of that type can measure everything from up to 100 Gs, or if we were looking into pressure specifically, 10 to 100 megapascals. Whereas something is like a hot filament ionization gauge is more optimized for vacuum chambers, so it's dealing with much smaller levels of pressure. So we can using our entity class here of pressure measurement devices, we can get all the names in the normal ranges for these devices. And after sifting out any that lack normal ranges for us to look at and converting those into pascals, we can then plot out the normal ranges for these different pressure devices. So we can see the piezoelectric sensor is actually towards the high range of pressure gauges that we have available. We have a lot more optimized towards low pressure devices, where it can be very important to know just what is the pressure that you're looking at. Now, looking at other measurement devices, the other end of the spectrum that I mentioned, particle detectors, we can also look at how different measurement devices are related, not just in what they measure, but also what they are an instance of. So we have things like calorimeters that will measure heat, but these are also used extensively in particle detectors. So they're an instance of a particle detector. In those cases, calorimeters measuring the heat that's given off by a particle that impacts it, which then can be used to determine the energy of that particle and thus infer other physical properties. But another particle detector is just a simple dosimeter, so which just might like the badge you might wear if you're visiting a site with a lot of radiation, just checking to see if you're still under the safe dosage of ionizing radiation. So, and then there are all sorts of specialized calorimeters that are used in a variety of different fields. So if we look at how all of these are related, we can start with our particle detector device and then look for what specific instances exist of those, and then the specific instances of those child devices in turn. And we can build sort of a tree here showing how all these devices are related. we might also look at those particle detectors and ask, well, what are the physical properties they measure? So we take our list of entities, and we ask about those measured quantities, and we can even pick out which ones, say, measure heat, which is the calorimeters. And we can also see in this family of particle detectors and related measuring devices, which quantities are most commonly measured. Obviously heat, because we have a lot of calorimeters, but also ionizing radiation, which is the kind of thing you want to check for, as well as a variety of other things. So energy is a pretty high one, same thing with count rate, and then you get to more specific things like electric charge. All right, and that is it for my examples, and I think I'll hand this off to whoever's next.
Thank you, Jason. That would be me. So we're going to look at excuse me, we already looked at particles. We're going to look at physical systems. So physical systems is a little bit different than some of the other domains we've looked at before, say particles, in that it's not going to be one of these sort of database lookup things where you're wanting to, say, find a specific mass, a specific number, get a specific numerical answer, that sort of thing. What we're looking at, and I guess I'll zoom down to the bottom here and then I'll come back, but let's say that the entity that I'm looking at is a charged triangular sheet. That's the example we're looking at here, and I ask for the electric charge density. Well, of course, the electric charge density on a charged sheet is a function of position. In this case, it's a very simple function. It's a constant on the surface of the sheet, and it's 0 elsewhere. So you see this piecewise bit here. The Dirac delta here is to say that you're within the thickness of the sheet, and then this piecewise says that within the plane that the sheet lies in, you're actually on the sheet itself. It's Q over A, because we're assuming this charge is evenly distributed, so it's just a constant Q over A if you're on the sheet, and 0 otherwise. But you notice that what we've done is we've taken okay, it would be nice if maybe there were a little more details here that I could show you. I'm not going to call them up since we're running out of time, but the actual physical system, the formulas depend on, say, the position you're at, say in XY, in terms of X, Y, and Z, and the position of the 3 corners of the triangle and the charge on the triangle. So those are the input parameters, but you see up here, our formula involves some sort of intermediate variables or auxiliary variables that depend on the more fundamental variables here. X3, Y3, and Z3 would be the coordinates of the third corner of the triangle. So we've just compressed them and called that a vector P, and we've made some other substitutions, like the center of the triangle is at this position. And then the formula up here, the actual formula, is just this bit, this first line, and then you can see an inactivated replace repeated. So it's a little tricky to use, and I encourage anyone who's interested in using these to look at the documentation page for the entity domain. Of course, all these entity domains have their own documentation pages. But at any rate, so there's some subtlety in using this. But just to give you a sense of the sort of scope of the domain, here are the types of physical systems we have, at least a sample of the entity classes. You can look at a sample of the entities. But here with the massive triangular sheet, we're going to, as I say, use the formulas, including the formula for the field. You can see that, of course, for a charge system, one of the things you're interested in is a field. And I chose to look at the field for 2 equilateral triangles. So first I define my equilateral triangle graphics object. Then I did that substitution into the formula above, which, as I said, is not trivial, but you can sort of see how to do it from the example. And then you get this pretty complicated result, but this is an exact result. And so that's pretty cool. It's not numerically, it's computed sort of a priori from first principles exactly. And then just this, this result doesn't mean too much to me because it's a lot of math, but if I want to visualize it, we're going to use the Wolfram language function stream density plot to visualize the field lines. We will build a manipulate so that you can change, say, what I've done is just to give sort of a nice picture, I created 2 triangles with different charges, different orientations, and I created a manipulate that shows how the field lines change as you change those various parameters, like the displacement between the triangles or their relative angle or their charge. So if you actually were to evaluate the code that's behind this click here, in your session, you'd be able to play with these sliders yourself. Instead, since this is a static web page, I just created a movie, and you can see what happens when I, change these sliders, and then the Wolfram language manipulate knows how to interpolate between the different slider settings. So anyway, so it just shows you the power of what you can do in a more formulaic basis. And so now I will end my share and hand it over to Eric Weisstein, I believe.
Yes, let's see, share. Hello, my name's Eric Weisstein. I do a number of things at Wolfram Alpha, but 2 of the main ones are the Wolfram Alpha unit system and math and physics related entities. So something big happened in May of this year. I know the US does not use the SI system together with 2 other countries in the world, but units and SI units in particular are still very important to anyone who does technical measurements, computing, etc. So in order to actually motivate this a little bit, because some of the implications are a bit subtle, I'm just going to go through before going through the actual marketing pages, a short summary of what actually happened and why, if you should care, and what it meant to the Wolfram language and Wolfram entities. So on May 20th of this year, the first new edition of the official document that defines what SI units are was released. It's the first time it's happened since 2006, so it's an unusual event. And the other thing that was significant about it is that it completed a process begun back in 1960, when the SI was first formalized in this way, of basically defining all units in terms of physical constants that are things that can be measured in any lab in the world, independent of time, independent of nationality, and all those things. So since 1960, this process had happened for 3 SI-based units already. The second, the luminous, the candela, which is a measure of luminous efficacity, slightly obscure unit, but still one of the best base SI ones, and the meter. So, but until this year, there still remained a physical cylinder, kilogram, stored in some ultra protected vault somewhere in Paris, that defined what the kilogram was. So obviously that's a little hard to reproduce unless you go in and get your hands on the kilogram, which they in fact deliberately don't let people do very often. But as of this redefinition, this kilogram can now be retired, taken out of its vault, put in a museum somewhere. All SI units now are wholly derivable from universal natural phenomena, which can be universally measured. And one important thing to emphasize is that the net result to almost everyone in the world who uses units and SI units, it's designed to be nothing. So they redefine them, but the new definitions are so close to the old ones that you couldn't measure the difference with current technology. The expectation, the hope being that with future technology, you actually could. So to summarize, prior to 2019, earlier this year, there were 3 SI base units that were exactly defined. As of this year, 4 more are, so that's a total of 7, and those correspond to the 7 so-called base SI units. So what are the consequences? Well, as already said, the SI units is now constructed entirely using physical constants, no more meter sticks, no more kilogram objects. One other interesting and slightly subtle thing to note is that while lab measurements will continue to improve, the value of SI units, or sorry, the value of physical constants when expressed in SI units is now fixed in stone. So even if you measure something more exactly, its value in SI units stays the same. It's the magnitude of the SI units that changes slightly. So slightly subtle but interesting point. it has an effect on uncertainties of physical constants. I already mentioned it avoids discontinuities. For most units that you will encounter, because the relationship of SI units did not change, you will not actually see any difference. There are, however, a few non-SI units that are defined in terms of fundamental constants, such as the electron volt, where you will immediately see this effect. So I think that will conclude my sort of background. And now let's go to the marketing page. So there are, now, since I've been talking mostly about physical constants, let's actually bring the units into it now. But the way to do that is to start again with physical constants. In version 12, there was a new entity domain added, the physical constant entity domain. This contains information about hundreds of physical constants, and what's more, it contains historical information. So as measurements improve or definitions changed, there you can get your hands on a set, basically an association that has historical values of these as they change for all the places where it's been curated. And the 7 important ones for the new definition of the SI, of course, among those. So I can get, using this SI exact constants physical constant entity class, a list of the ones that are now used to define SI. And with a little utility function, I can say, okay, pull out the ones corresponding to a specific property and a specific standard. And so the standard I picked, CoData, is sort of a standard place where people define, it's an international group of people that get together and find the best possible values to use for physical constants. Before, earlier this year, this is what these things looked like. So they had values and they had certain standard uncertainties. Notice Planck constant here. It's just some number with some number of decimals, and it has a fairly small uncertainty. All of these actually have fairly small uncertainties, which is what actually makes them desirable for defining units, because you can measure them so exactly. And now, in the new world, you can see that the Planck constant is no longer some numeric thingy with precision, but since in Mathematica a fixed number of digits exact means a rational number, it's this exact rational number. And so all the constants, when expressed in SI units, now take on these rather odd looking rational exact values. So I said these are used to define the SI. How does that work? Well, I just define a couple little utility functions, pull out the definitions from the physical constant table, and I can look at the equation. So the meter is now defined, and actually was before as well, as an exact number of meters per second. So that gives a relationship between meters and second. The second is defined exactly in terms of a constant involving hyperfine splitting of a cesium atom, and so forth. But the interesting thing is now you see these new guys. The Planck constant now gives a rational multiple of things that look fairly familiar, kilograms, meters, and seconds. So the way we get from the constants back to the units, as promised at the beginning, is basically by inverting these 7 sets of equations, which is done right here, where there is a solve. And here are the new definitions of the ampere, the candela, the Kelvin. So you measure this guy in the lab, you measure this guy in the lab, and you multiply by a certain prefactor. That is, for all times, the definition of the ampere, and can be done with all derived SI constants, including non-base ones as well. So that looks a little intimidating, and in fact it is. Maybe it looks a little less intimidating if you factor them. But so this, it matters. I want to show you one quick example too. So I said you probably wouldn't notice any difference for most units. An electron volt, this is what it would look like on Wolfram alpha. Now that we've gone through and made all the changes to actually make things exact, you can see that you get a little exact button, and it shows you the electron volt, which is defined as the energy that one electron charge takes in increasing a potential of 1 volt, actually becomes an exact number. And if Wolfram alpha were responding now, you would see that this is some very nice rational number. And
Eric, I don't know if force refreshing the page might help. Sometimes it does when it does
yeah,
that. I think you're pointing to current too, so I don't know if production would be better.
It might be. It might be. Let me go back here. Probably somebody's pushing the site. Okay. And there we go. Show exact values. There we go. This is the guy in question. So, short summary. The entire Wolfram Alpha and Wolfram language unit systems have been updated for this important change. It will not make too much of a difference to most users besides seeing these weird rational things show up, but it is actually a very important step in terms of unifying and moving forward with making the SI system universal, not dependent on man-made artifacts. And it basically, if we've done our job right, as I said, you will not notice much difference, but there's actually a fair bit of difference under the hood required to support and handle these correctly. And that is, I think, all I wanted to say. So I guess I will hand back to Jeff or whoever is going to be our closer.
Yep. So I think, yeah, we've gone just only 5 minutes. Not bad for all the people we had to switch back and forth between. So I think we've covered all the items on this page we were intended to. So thank you, everyone, for attending with us. Hopefully, you have at least a little bit better insight as to what these pages are talking about if you didn't follow along yourself. But all the examples were presented are on those pages. All you have to do is click on them, and they automatically copy your clipboard, and you can paste them straight into your Mathematica session and evaluate them at your leisure. For the time we had in the thing, we couldn't do that for everything, but it's basically the same material we were working with, so it's all available to you there. So hopefully you found this session useful, and I think that should be it. Thanks again.